Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 6.3, which introduces you guys to the concept of the kernel and the range of a linear transformation. To do this, what we're going to do is we're going to state and talk a little bit about a very important theorem that discusses the dimension of the kernel and the dimension of the range of a linear transformation and how they relate to the dimension of the domain. And then we're going to look at a couple of examples of sort of using this theorem to describe the kernel and the range of a linear transformation. So let's go ahead and get into this. So this is what's called the general rank nullity theorem. Remember, we discussed and actually proved the rank nullity theorem back a while ago when we were talking about the null space, row space, and column space of a matrix. And this general rank nullity theorem basically extends that concept. So what it basically says is we're going to let T be a linear transformation from V into W, where V is a finite dimensional vector space. Remember, being a finite dimensional vector space just simply means that it has a finite sized basis. So in other words, there is a finite collection of vectors that could be used as a basis for V. Then this general rank nullity theorem says that the dimension of the kernel, so the dimension of the subspace of all the vectors in V that get mapped to the zero vector in W, plus the dimension of the range of T, so the dimension of the subspace of W of all the vectors that actually have something in V that gets mapped to them. If you sum the dimension of the kernel and the dimension of the range, you must get the dimension of the domain. And what's really interesting about this is that this actually is just a direct extension of the original rank nullity theorem. The only difference there is that we were talking about matrices. And there we called the kernel the null space, and we called the range the rank, and the dimension was just simply the number of columns in the original matrix. But in this case, we're basically saying this can be extended in general to linear transformations. Now, your book goes through a pretty detailed proof of this, and I think that proof is pretty interesting. But again, it sort of goes a little bit outside the focus of our class. So we're going to just state this, and I hope that what our work in working with the normal rank nullity theorem for matrices hopefully justifies this statement enough so that this is sort of believable. Another way that I hope you guys can sort of understand this without a formal proof is that what this is sort of saying is if you sort of rewrite this, you can sort of see this as saying that the dimension of the range of T, so the dimension of the range, is equal to the dimension of V minus the dimension of the kernel. Now, the reason I sort of want to state it like this is I want to sort of you guys to think about is that the dimension of V tells you how large your domain is. And what this is saying is if you know how large your domain is, and you know how large the subspace is that gets mapped to the zero vector, almost imagine it as all those things that get mapped to the zero vector sort of get smushed together. Well, what remains if you take the difference of how big your domain is from how much stuff you sent just to the zero vector, then what remains is your range. In other words, we're basically saying all the stuff in the kernel gets thrown out and just mapped to the zero vector. So the difference in sizes between the dimension of everything and the dimension of the stuff that just gets mapped to zero is really the dimension of the remaining range. And that hopefully gives you guys just at least a little bit of a verbal understanding or just a way of thinking about why this theorem sort of makes sense. If you guys want a formal proof, your book does go through at the end of section 6.3 and formally prove this in general on using a couple different cases. It's not a particularly bad proof, but it is just sort of lengthy. Now, what I'd like to do, instead of doing that proof, is to look at a couple examples, specifically usually in this sort of form, that'll really help us understand the range and kernel of a transformation. If you remember from the previous video, we saw that it was pretty easy to figure out the kernel of a transformation, but using this theorem will also make it pretty easy to figure out the range. So let's go ahead and look at those examples. So, here's our first one. We're going to consider the linear transformation that goes from P3 of R, so this would be from the polynomials of degree 3 or less, into P1 of R, which is the polynomials of degree 1 or less. And it's defined as you start with a polynomial and you map it to its second derivative. So what we'd like to do is we'd like to determine a basis for the kernel and state the dimension of the kernel, and then determine a basis for the range and state the dimension of the range. So let's go ahead and start with the sort of kernel here. So remember that for the kernel, we need to go ahead and figure out everything that's going to get mapped to 0. So we want to set up the equation t of p of x is equal to 0. Now, when we say 0, we mean 0 in p1 of r. So I guess we actually mean 0x plus 0. So we wanted to find out everything that sort of solves this equation. Now, what is p of x? Well, p of x is something from p3. So we can sort of think about that as ax cubed plus bx squared plus cx plus d is supposed to be 0x plus 0. Okay. So now let's go ahead and actually apply our transformation, which is supposed to be that we take the second derivative. So if we take the derivative and then the derivative again, looks like this guy should come out as 6ax plus 2b. And then, of course, when we take the second derivative of these, that just drops out. And that's supposed to be 0x plus 0. If you notice, what that basically tells us is that 6a is supposed to be 0. And 2b is supposed to be 0. In other words, a is supposed to be 0, and b is supposed to be 0. So what that tells us is that the kernel of our transformation are all the elements of this form, ax cubed plus bx squared plus cx plus d, where a is 0 and b is 0. In other words, it's everything that looks like 0x cubed plus 0x squared plus cx plus d. Or if you prefer, a nicer way to represent that is just cx plus d. So there is our kernel. And this should make sense. What is this really saying? This is saying that the kernel of this transformation are all the linear polynomials. Because if you have a linear polynomial and you take the second derivative, you're going to get 0. All right, what's a basis for the kernel then? Well, since we have this nice general element, we just set one parameter, say c equal to 1, all the other parameters equal to 0, and then move down the line. So it looks like a basis would be x, that's letting c equal 1 and d equal 0, and then 1, letting d equal 1 and c equal 0. So the basis for the kernel would be x and 1, so that can build any linear polynomial, and that would tell us that the dimension of the kernel of t would be equal to 2. So we now know what the kernel looks like, a basis for the kernel, and the dimension of the kernel. All right, now let's talk about the range. But for the range, since we know the dimension of the kernel, let's figure out the dimension of the range first. So by the general rank nullity theorem, we know the dimension of the range of t is going to be equal to the dimension of our domain. Remember, our domain is P3 of R. So the dimension of P3 of R minus the dimension of the kernel. Well, that tells us that the dimension of the range of T is, well, the dimension of P3 of R is 4. And the dimension of the kernel we just found is 2. So that means the dimension of the range of t is equal to 2. So the dimension of the range is equal to 2. Now, this tells us everything about the range. Why is that? Well, think about what we said about the range. The range is supposed to be a subspace of the codomain. But what was our codomain? Our codomain was P1 of R. So what's the dimension of P1 of R? The dimension of P1 of R is 2. So that tells us we have a subspace that's the same dimension as the overall space. But remember, if you have the same dimension as something you're a subspace of, you're the same thing because you can't fit anything else that's the same size. So this tells us, since the dimension of P1 of R is equal to 2, this implies that the range of our transformation is equal to P1 of R. In other words, everything is in the range. Everything in that codomain is in the range. Well, that makes it very easy. Well, what's a basis for P1 for the range then? A basis for the range of t? Well, a basis for the range of T is a basis for P1 of R. Well, basis for P1 of R would be something that looks like 1 and X, right? That's how you build everything that's in P1 of R. So there we go. We've now figured out the dimension of the range, which we did through the general rank nullity. We also figured out that the range is just equal to the codomain, and then we were very easily able to state what the basis for the range would really be. Now, this is just our first example of this, so we're going to quickly run through a couple more. What I want you guys to sort of see here is that for the kernel, when we're working with the kernel, we really solve things directly because the kernel basically gives us an equation. It says T of a vector must be equal to the 0 vector. So whenever you're working with the kernel, you can expect to just basically set something up, solve it, and use that to figure out what the kernel looks like. Then once you know what the kernel looks like, figure out a basis, and then figure out the dimension. Working with the range, we almost work in reverse. Once you know the dimension of the kernel, you'll automatically know the dimension of the range. Once you know the dimension of the range, then you can really think about what does the range look like and what's a basis for it. So we sort of work in reverse there. All right, let's take a look at another example. All right, so now we're going to consider this linear transformation. It's going to go from R3 into P2 of R. So we're going from the three-dimensional real vectors into the degree 2 or less polynomials. And it's defined by taking T of ABC and mapping it to A minus BX squared plus CX plus B minus A. So again, let's start with the kernel. All right, so for the kernel, we want to set up T of ABC is supposed to equal the 0 vector in P2 of R, which in this case would be 0x squared plus 0x plus 0. So what is T of ABC? Well, according to this, it would be A minus B x squared plus CX plus B minus A. And that's supposed to equal 0x squared plus 0x plus 0. All right, that gives us some equations. It tells us that A minus B is supposed to be 0. It tells us that C is supposed to be 0. And B minus A equals 0. If you want, right, I mean, these are pretty easy to sort of solve, but you could even set this up as a homogeneous system of linear equations. It is not a coincidence that every time you do this, every time you work on the kernel, you're going to be able to change it into a linear system of equations that is homogeneous. Again, that's because the kernel really relates to the null space of a matrix, so it's always going to be a homogeneous set of equations. In this case, if you wanted to, it's not hard to see that A must be equal to B, C must be 0, and of course this guy gives us that B equals A, so these two mean the sort of same thing here. So what this basically tells us is that the kernel of this is everything where A and B are equal and C must be equal to 0. So the kernel of T here is the set of everything. Let's just let A equal B to make that a little bit easier. It would be everything that looks like B, B, and 0. That would be our kernel. It would be all the vectors in R3 that have the property that their first two components are the same and their third thing is equal to 0. Notice that that tells us the dimension of the kernel of T. Oh, well, let's first start with a basis. So a basis for the kernel of T should be very easy. It would just have one thing in it. It would just look like maybe something like that, 1, 1, 0. Again, getting that by letting B equal 1, and there are no other free parameters. So that then tells us that the dimension of the kernel of T is equal to 1. So there we go. The kernel in this case is one-dimensional, and it just there's all the things that look like something, that same value, and 0. All right. Now, let's go ahead and figure out some things about the range. So let's start with the dimension of the range of T. Well, according to that general rank nullity, right, we'd have to use the dimension of this and then subtract this dimension here. So it would be the dimension of R3, which was our domain, minus the dimension of the kernel. Well, that would tell us that the dimension of the range of T is 3 minus the dimension of the kernel, which is 1. So the dimension of the range of T is equal to 2. Now, why is this so useful here? Well, let's think about this. So the range is dimension 2. Let's think about the codomain. The codomain, which is P2 of R, is dimension 3. So is the range equal to the codomain here? No. We know that the range is a bit smaller. The range is only 2-dimensional, but our codomain is 3-dimensional. But here's the really useful thing. The dimension of the range is 2, meaning that we know that there must be a basis for the range that only consists of 2 vectors. In other words, if you prefer to think about things in terms of free parameters, there must be a way of expressing the range of t in terms of only 2 free parameters. Said another way, if you look at what you're mapping, these polynomials here, there must be a way to express this in terms of only 2 parameters. Okay, so what this tells us is we know that the range of t are all the outputs. They're all the polynomials that fit this form. In other words, they're all the things that look like a minus b x squared plus cx plus b minus a. But this dimension tells us ahead of time that we must be able to reparameterize using only 2 parameters. And you guys should be able to see how to do that. If we let a minus b be t and c be s, then this guy is naturally negative t. So in other words, the range of t, with a little bit better of a description, is really tx squared plus xx minus t, because that b minus a is exactly equivalent to negative a minus b. So all I'm doing on this step here is I'm just reparameterizing from all 3 variables to 2. And I know that must be doable because of the dimension here. Then that tells us that a basis for the range of t, so a basis for range of t, well, just do our standard sort of trick. Let's let t be equal to 1. We'd get something like x squared minus 1. And then let's let xs be equal to 1 and x. So the range is everything that can be built out of things that look like x squared minus 1 and x. Anything that cannot be built out of x squared minus 1 and x is not going to be an element of the range. And there are going to be some things like that. So something like, just say, for example, like 3x squared is not an element of the range of t, because 3x squared cannot be built out of x squared minus 1 and x. And that should make sense, because remember, the dimension was only 2, and the dimension of P2 of R is 3. So there are some things in this codomain that you simply don't hit using this transformation. All right, let's go ahead and take a look at one more example. This will actually relate to one of the first examples we actually proved was a linear transformation. All right, so we're going to consider this linear transformation that goes from the 3x3 square matrices into the 3x3 square matrices, defined by as when you apply it to a matrix, you do that matrix minus its transpose. So let's determine, again, first a basis for the kernel. So for A, we're going to set up T of A is equal to 0. And by 0, I mean the 0 matrix in M3. So notice that that means that A minus A transpose must be equal to 0. So that means that A must be equal to A transpose. In other words, what we just figured out is that the kernel are all the symmetric matrices. So the kernel of T is actually equal to all the matrices A, such that A equals A transpose, and A is an element of M3 of R. Can we describe that a little bit more in detail? Sure, right? We can write it out as a general element. So we need to write out a 3x3 square matrix. So it looks like that would be something like A, B, and then we'd have to put a B there to preserve symmetry. C, we'd have to put a C there. Could put anything we like there. D, E, then we'd have to put E there, and F. So the kernel looks like things that look like that. 3x3 in size and symmetric. That tells us that a basis for the kernel of T would be things like 1, 0, 0, 0, 0, 0, 0, 0. That's letting A be 1 and every other parameter be 0. Then 0, 1, 0, 1, 0, 0, 0, 0, 0. Then 0, 0, 1, 0, 0, 0, 1, 0, 0. then things like 0, 0, 0, 0, 1, 0, 0, 0. Things like 0, 0, 0, 0, 0, 1, 0, 1, 0. And finally, 0, 0, 0, 0, 0, 0, 0, 0, 1. So that would be a totally fine basis for the kernel there. That would also tell us that the dimension of the kernel, T here, would be equal to 6. And again, we knew that it was 6 even from back here because it had 1, 2, 3, 4, 5, 6 free parameters, and our basis, of course, had 6 elements. Okay, so very interesting here. The kernel is actually a very special set of sort of matrices. It's all the symmetric matrices, which should make sense because what this transformation does is it removes the transpose of a matrix from the original matrix. If that matrix is symmetric, then that's going to result in 0. All right, let's talk about a basis for the range then and discuss the range a little bit. So we know that the dimension of the range of T, well, we can sort of do the same trick that we've been doing. It'll be the dimension of our domain. Now, in this case, our domain and our codomain are the same vector space, but we would focus on this guy, M3 of R there. So the dimension of M3 of R minus the dimension of the kernel. Okay, now that would tell us that the dimension of the range, well, the dimension of M3, those are 3 by 3 matrices, so 3 times 3 gives us 9, minus the dimension of the kernel, which is 6. So the dimension of the range must be 3. So that's telling us that there must be a way to write a basis for the range using only 3 vectors. In other words, a general element of the range must only have 3 free parameters. So let's think about what the range of T really looks like. Well, we know that the range of T is the result of A minus A transpose. So let's actually describe that more in general. So if we let A be the matrix A, B, C, D, E, F, G, H, I, that's a generic 3 by 3, minus its transpose, which would be A, B, C, D, E, F, and then G, H, I. That would then tell us that the range of T, if we actually perform that subtraction, would be things like 0, B minus D, C minus G, D minus B, 0, F minus H, G minus C, H minus F, and 0. Okay, that is a description of the range. But we can do better than it. How do we know we can do better? Because the dimension of the range is 3. So there must be a way to write this with only 3 free parameters. And you can see how that would work. If we let this guy, and this guy be 3 different parameters, call this guy maybe T, S, and R, then this is going to be negative T, this is going to be negative S, and this is going to be negative R. So we can reparameterize and call the range of T actually everything that looks like 0, T, S, negative T, 0, R, negative S, negative R, 0. Now again, the whole trick of this is that this is much easier to do, not when you just look at this, but when you look at this, plus you already know the dimension. That's what makes this much more doable. Now, what is this really describing here? Well, you guys should know that this is actually describing the skew symmetric matrices. So the range in this case are actually all the skew symmetric matrices. What's a basis? Well, we could say a basis for the range of T should just be things like 0, 1, 0, minus 1, 0, 0, 0, 0. Something like 0, 0, 1, 0, 0, 0, minus 1, 0, 0. And finally, letting R be equal to 1 and everything else 0, 0, 0, 0, 0, 0, 1, 0, minus 1, 0. And there we go. We found our basis for the range, which has 3 elements, as guaranteed by the dimension here. So that wraps up our discussion of section 6.3. Hopefully that helps you guys understand the concept of the range and the kernel a little bit more. In our next video, we'll be moving into section 6.4 and finishing up our discussion of linear transformations and understanding a few more properties of these transformations.